Okay, so we're talking about essentially how you could implement generic data structures in C. And generic data structures in C are difficult because we don't have things like generics in Java. They're replaced with instead the notion of void star in C. We don't have a notion of things like generic comparator types that we can use to pass to things like sort methods that sort things of a specific type that that comparator is customized for. We don't have that stuff in C, but we do have function pointers. So that's what we're going to be investigating here. So first we're going to look into function pointers for being able to provide generic operations on data structures that actually understand what types are being stored within those generic data structures. And then we're going to look at structs of function pointers to provide some notion of polymorphic behavior, and we're going to look into xv6 code to see examples of that. And I'm not going to talk about, but I wanted to list here, that a lot of C code will use macros for generating functions that are specialized for different types. This is a kind of very ugly approach that's hard to kind of understand visually, so I'm not going to go through it here. So we're going to look at these first two. You aren't going to see macros within the class, but you will see both of these types within the class. So let's start out with going over how you use function pointers to get some notion of how the data within a data structure can, for instance, be compared. So the goal is that we want a data structure to hold some data and be able to intelligently compare that data, but in the case where your data structure itself is generic, like your list. It doesn't know what the type of the data is in it, so it should work regardless of the type of data that it contains. But we kind of have a catch-22 here. If the data structure doesn't know the type of the data it's containing, how can it compare values of that type? So first, let's look at a man page, a manual page, for a place where we see this type of API existing within C already. So we're going to look at the man page for qsort. So qsort is a API that, as you can see, says, yes, use it to sort an array. Fine. It's within standardlib.h, and its API essentially takes some void star. Again, it doesn't know what the things are that it's sorting. It's just taking a void star. It's saying within this void star, how many members are there, and what is the size of those members. So these are just used for kind of iterating through the array in an appropriate way. I'm not going to go over that. What we care about most is this right here, which is the syntax for saying, here's a function that you're providing as an argument to this function. This function that you're providing, we're going to call a variable compar. I don't know why they dropped the E. It's a very Unixy, annoying, dumb thing to do. And it takes two void stars as arguments. Hopefully those void stars are the same void stars as are stored within this data structure. The client better use this API correctly in that way. And the int that it returns is essentially -1, 0, or 1, depending on whether the first void is less than, the same, or greater than the second void star. So this is what it looks like to have an API where we're providing some sort of a custom comparison function that understands the void star types that the base holds. So this is what it looks like. And you can actually see that this looks a little bit similar to what we saw before in the Java implementation, right? So we see something that looks a little bit like that. The C equivalent, right? So you can see some similarities here. In both cases, we're taking in a list. Java collections are nicer than C kind of generic types, so you condense what's 3 arguments into 1. And then we take some sort of a user-provided comparison thing. In Java, it's a weird kind of object that provides comparisons. In C, it's a function pointer. Okay, so we see that there's kind of this equivalence between the two things. Let's actually see what that might look like if we were to implement lists. So let's exit out of this man page. So I have, what did I call this? Oh, function pointers.c. So I've implemented the shell of a very, very simple program called function pointers to test our function pointers. And it is implementing a simple generic data structure that does sorting. So I'm calling the whole API the sorter API because I'm very, very original. So I just have created an initial structure for it. Whenever you're implementing anything in systems, implement the data structure first. Everything else comes from that. The idea here is that I'm going to have some array that's going to hold data. That array is going to be of a certain size, and the data within it will be from some start index to some end index. We'll get into the details of that. It's not that important. Then I have create, destroy, add, and get. The difference between what you all are doing in your linked list is, one, this isn't a linked list, so I'm not giving you the answer to the current homework, and two, this add function is also going to sort the array, ensure that whatever we're adding, we're kind of implementing one iteration of the insertion sort on it. So we're going to add the value to the data structure, but ensure that it is added in a sorted location, right? Now, the current API takes integers as values, so it's not a generic data structure. Right now, it just stores integers. And you can see get will return kind of those sorted integers from lowest to highest, and it returns an integer. So I believe that this API works, or that this, yes, okay, great. So right now it's not doing anything interesting because it doesn't have an implementation. Get just returns 0 independent of what we've added in, and I've created a very simple test program that is completely insufficient for actually testing it, as sorter create, and it's going to create a sorter that can sort up to 32 items, and we can add items into it and then get them, printing them at the same time. So this is just typical, C stuff. So let's very quickly go through and implement these things. So in sorter create, we want to allocate the sorter structure. So I'm going to do a struct sorter, I'll call it S. I'm going to malloc that, and of course we want it to be the size of a struct sorter. As I told you all, we absolutely want to check to make sure whether malloc returns a valid value, i.e. a non-null value. In this case, unlike in your specification, if S returns null, I will actually just return null. This is what you see a lot. So sorter create in this case may return null, and that means that the client has to deal with this failure, which is generally a better API design. Otherwise, we're going to say that our I'm going to initialize our S. I'm going to use some syntax that you may not know. It's just another syntax. It doesn't matter that much. So struct sorter. So a dot and items is equal to n, and dot start is equal to 0, and dot end is equal to I'll say 0 as well because it has no items in it. And I do want to allocate a second thing as well, which is data. So S data equals malloc, and this is size of int times n, because we're gonna sort those n items in it, right? So now, of course, yes, I need to kind of redundantly go through here and do all of the checks to make sure that everything is happening correctly. However, if I just do what I have here, this is actually incorrect code. it's incorrect code, and valgrind will tell you that it's incorrect code if it were able to test it well, because I actually need to free the S before I return. If the data didn't allocate, then I'm not going to use the sorter that I previously allocated, so I better remember to free it. This ends up with really tedious, annoying code, and please read the composite style guide for ways to kind of make this prettier and nicer. Okay, and then the data. Oh, I already initialized that, so we don't need to do that. Actually, I'm gonna make this a little more uniform. Let's clear that up. So int data equals int data, and then just data equals data. And then here we'll keep it nice and uniform, so we're initializing data to the data itself. Code craftsmanship is really important, so making your code actually just look nice actually makes it easier to read. So this makes it easier to read. If we have a new structure called S, we're initializing all the items in it, and you can see that it's very easy to just go down one after the other and see what things are being initialized to. So now, of course, we want to return S itself because we have initialized it. So great, let's create. It may or may not work. Let's actually test it. I don't need to actually have all of my code working to test one part of it, right? I didn't make a correct makefile, so this actually doesn't work correctly. So I did something dumb up here, which is this. I'm going to make that that. Great. Okay. So it compiles. It runs. I could kind of, because I'm just testing, I don't need to maintain a nice boundary where my client testing code isn't reaching in and accessing my data structure. I'm just getting stuff working initially. So I might go through and actually make sure that everything's getting initialized correctly. So I might say let S has an items and an array at the address there. So I can say s.n items and s data. So again, I'll make it a little bit nicer, in this case to C. Oh my god, that's going to get old. So instead I will do that and that. Okay, and then run it. And we can see, oh cool, actually it did create the data, and it allocated a whole bunch of stuff and initialized it, hopefully correctly. I haven't really tested that everything works well in create, but I've tested that the main initialization is actually working, and that everything kind of compiles and runs correctly. So that's what I'm shooting for. That's what I want. I'm actually going to, again, code craftsmanship is a really important thing. I'm going to try to make this all look pretty uniform. So now you can see I've segregated my code for doing that and testing it. I've segregated my code visually for doing the code for allocating that and testing it. And I've segregated the code for initializing everything. Keep everything clean, keep it easy to read. That's what we try to do. How can I create this split window? That's, I don't know, it's just Emacs. That's what it does. If you're using Emacs and you're using my configuration file, creating the split window is just Control X2. Nope, sorry, that's splitting it that way. It's muscle memory at this point, so unfortunately I can't often remember. So Control X3 splits it that way. Control X1 gets rid of the split. Control XO goes to the other workspace. So, you know, we can talk about all of that later. I did want to demonstrate writing some code here so that you see the mental process that goes into it, and I wanted to demonstrate using an editor correctly so that you see what editors should be used to do. Bushi Codes asked a really good question that, you know, is there a way to kind of I'm returning null here, I'm returning null here. It seems like we're copying or making redundant code. Can you use gotos to do that? Yes, that is the only valid good use of gotos, and it is, I think, the correct way to do it. I will make a note here. Read the composite style guide for a way to make this code generic and shared with other error paths using gotos. You may have heard gotos considered harmful. This is an old paper by a very smart person who is correct. Gotos generally are an absolutely horrible idea, and you shouldn't use them. There is exactly one reason to use them, and that's as local exception handlers, which is what I'm suggesting here. So I know this looks really ugly here. Never ever would I use a console that is as thin as this, so it just looks bad in this situation, so I apologize for that. But okay, so let's go on to destroy. Destroy, I'm going to do the simple thing and destroy. So, but before destroy, I do want to kind of have the same error checking that you had in your linked list. So I'm going to add an int instead as a return type, so we can error if there are things stored in the data structure. But to understand what some of the variables mean, I think we're going to move on to sorter, add, and get. So for add, we're passing in an s. Let's say as part of my specification for this, I basically say that the user should always pass in a valid sorter to these things. So one of the first things I do is add and assert that s is non-null. And you can see at the top of my file, I have included assert.h. I pretty much kind of muscle memory include that in almost all of my projects because, I mean, you should use assertions a lot. So I'm asserting that s is valid. I'm going to do the same thing here because I know that I'm going to want to. And then, hey, I know that I'm going to want to here as well. So let me just add those in. Again, this is, I'm assuming, invariants. The invariants in this library are that the client always passes in a valid sorter. So I'm just doing that checking here. This is, asserts are just there to help debug things. They should never, ever trigger. Ever, ever. You're making a strong assumption about the code, and a failure of assertion means that something has gone drastically wrong. Okay, so add. Let's look at add. In add, fine, I have my sorter. I could do some error checking. I'm going to actually avoid that here, so that's bad. So, you know, I'm bad, sure. This isn't the homework. I'm not grading this. I just want to move on. So I want to add something in. To add something in, I have to take my array that's in data, and actually I'm going to save that into a local variable so that all this code gets a little bit easier to read. And actually I don't think it's a void star. Yeah, it's an int star. I made it an int. So it will be a void. I'm kind of already skipping to the next step. So I have an int, and this is my array. I'm just going to keep the names pretty simple. And just to, again, kind of better document what the code is doing, I'm going to say the number of items. I'm going to have that there, because I don't want to use this error operator every single time, right? So I'm going to say my array is that. I'm going to say my n item, is s n item. And great. If actually I'm not going to do error checking, so I don't need the n item. Easy, great. So I'm going to define my start as my start value. I'm going to define my end as my end value. You'll see what these are doing. I'm not gonna go over kind of what they're doing right now. It's fairly mechanical. I'm making some arbitrary decisions here. Don't worry about it. at least what I know is that start and end are 0 because that's how I initialized them when I created the thing, right? So the start is where the start of the data being stored in the array is. The end is where the end of that data being stored in the array is. Easy, easy. So I need to implement add. I need to put something into the data structure. I have easy easy variables for accessing all of the things that I need. And now all that I really need is to kind of iterate through the array and do the right thing. So I'm going to generate my variable I for I equals 0, I less than SN items. That's actually wrong, so I'll change that. So that should be E minus S. I know that I'm going to insert an item, so I'm actually going to say that I'm going to put the end as one past what it's currently holding. I know I'm adding something else, so cool, this is kind of my new end. New end after adding, right? Cool, okay, fine. So what I'm going to do is I'm going to go through the array, and I'm simply going to say if I'm going to do a comparison, right? I know I'm holding integers. I'm supposed to add in a sorted way. So how do I do that? Well, I have to do a comparison between the integers to see if I should put the integer into the current slot that I'm looking at or at another slot, right? So fine. I'm going to say that I'm going to look at Ri. So I know within the array at that index, I want to see if Ri is, let's say, actually, you know what? I think I'm going to just make this code all, no, I don't want to make it dead simple. This is perfectly fine. We'll go this way. So I want to see if Ri is less than val. If it's less than the value, if we're sorting it from lower value to higher value, then I know that I want to go to the next item in the array, right? So I might continue there. I might invert the if so that I handle the case where I do want to actually flip them here, right? So, okay, in this case I'm saying, well, I know that Ri is less than val, so I should go on to the next value in the array, therefore let continue. However, if Ri is, if the value at the ith index within the array is actually greater than or equal to val, then I actually want to do a swaparoo, right? So I might create a temp variable and set the temp variable equal to Ri. And then I can actually just use that value directly. Maybe that's a good value, maybe it's not. I don't know if the temp variable name is providing more information that helps us make a good decision there. Probably not. So in this case, what I want to do is set Ri equal to val, and then val equal to temp, and then continue with the next iteration. So I'm essentially using val not only as the input, I'm also just using it as the value that I keep moving later and later into the array until it's in its proper spot, right? So hopefully this makes a little bit of sense. I'm going to have an error condition here on the last value. I hope people might see that, but if not, we'll actually run it this way and see where the bug happens so that we can actually kind of debug it a little bit. So I don't know if this is going to work. You know, I just kind of quickly wrote some code, so I'm going to just go through and kind of print out everything that's happening. Yes, people do actually just debug by printing sometimes, and in very simple programs like this, sometimes it is actually the easiest way. However, you want to make sure that all of your printouts are fairly well organized. So I'm going to say, yes, this is in sorter add, and I'm going to say that we're comparing value that versus that, and very neatly indicate what the printf, the printout is actually comparing, right? So I'm gonna go there, and I'm gonna maybe just do that for now, and hopefully we'll kind of get to see what happens as the program runs. So let's try to actually do this. Yeah, I have errors, not surprising, that's fine. I want to emphasize again, I haven't implemented my entire linked list. I've implemented one function at a time, and I'm testing them one at a time. There's absolutely no reason to implement everything, make a whole bunch of errors, and then have to change everything. Figure out a way to implement it one thing at a time, debug them, and then move on to the next thing. Okay, so function pointers 55, so go to line 55, and S is redeclared. Yeah, I'm an idiot. So that can't be the sorter, of course. It can't be both the sorter and the start. So I will not be lazy and actually type things out. So now S start, I will line everything up to keep it looking nice. And notice, it doesn't take a ton of time to make things look nice. You aren't saving time by making them look bad. You just make it look nice because it's easier to read and debug and live with. So just do it. Oh, hey, okay, compile. That just kind of worked. Great. But let's see if it really worked. So we're comparing 0 with 3, then 0 with 1, then 0 with 2. Ooh, this is weird. What is happening here? So first, we're comparing a lot of 0. We're seeing that a lot, so that is probably the problem. So let's kind of look at what might be happening here. We have compare. We're always printing out 0 in temp, so we know that the item at the start of the array is essentially always 0. If you remember, we're calling sorter add 3 times, and we're kind of coming through here and doing lists essentially 3 times, right? So we're calling sorter add and we're printing out 3 times, which means because this is happening 3 times and we're calling sorter add 3 times, we're actually only going through this loop 1 time every single time we go through. Okay, that's somewhat predictable, right? It's predictable partially because we aren't actually really changing the end within the data structure at all. So maybe we could actually fix that by saying, let's actually change the end value to be our new end value that we've computed, that is itself plus 1, right? Great, okay. So maybe that'll change some stuff. Hint, it's still broken. So, one bug gone. Now we're actually running through and executing this probably 1 time when we pass in 3, 2 times when we pass in 1, and then 3 times when we pass in 2. Awesome! It's actually iterating an increasing number of times every single time we call add. So it thinks that it's starting to add values in. That's real good. However, still problems, right? Still problems because, like, what we have the 0. Recurring 0. We have problems. So why is recurring 0 happening, right? We effectively are never... I don't want to come up with some complicated way to say it. I just am going to say what likely seems like it's happening is maybe we aren't getting to this location, right? So if we aren't ever adding new values concretely into the array, then we're never going to get to that spot, right? So here, post compare, we are found a lower value. Okay. So let's check. Compiles, runs, yeah, okay. I had a hypothesis about what might be going wrong. I added a test to see whether that hypothesis is true. Yes, we are literally just never getting here, right? So that's not great. That's not good. I want to point out, if I misspell something in a comment, ooh, my editor is good enough to realize that comments are English, so I can use spell checking. Now you see at the top of my window, it's giving me the suggestions for edits, ways to fix my spelling. Yes, I would like the 0 option there. Your editor should be doing this. You should not make spelling errors in comments because your editor should be detecting that you're doing that, right? Okay, so we aren't getting here, which means that the value in the array is always less than the value being passed in, right? So this just, yeah, seems like a logic error that we have. Any suggestions on how to fix this? I'll give you a little time. I hope that I'm not just kind of going off the deep end and going into too much complexity in all of this, but I figured going through an example of how to use an editor and how to go through a mental process of writing code would be useful in addition to the main stuff that we're talking about. Any ideas? Okay, so we have somebody that says, can you just print each value in the array? I can tell you what each value in the array is. We know that we're never getting here. Therefore, we know that we're never adding a value into the array here. So therefore, we know that the array is never adding anything into the array ever. So the array holds only what malloc initialized it as. And I will say that we already have a bug. Valgrind would get angry at us because we are accessing memory that has not been initialized. I allocated this array to hold the data, and lower down I am accessing the values of it, and I have not initialized the values within it. So I should do that. So I will do that. So once we know that we have the data in sort or create, I'm now going to go through. I'm going to create my I. I'm going to have a for loop, as one does, equals 0 while I is less than n, less than n I plus plus each time, adding that, and then I know that I want data at I to be initialized to some known value. The question is, what known value? And I'm going to actually set it equal to max int. I'm not really going to go over why. Just know that it is the largest int value. I don't know if that's going to compile because I might need to include another header file. Yes, I do. So let me actually look in the man page for max int. Ooh, it does not have a man page for that. Let me... I honestly just completely, I'm not jiving here. I just don't remember what include I need for that. I think it's limits.h, but how do I debug? I think it's just limits.h, but let's see. Oh god, I can't click on it there. Yeah. Limits.h, great. Okay, so let me go back. Great, limits.h, let's go back and try to compile. Nope. Okay, now I'm confused. Undeclared, did you mean max input? No, I meant max int, trust me. Int max, thank you. Good job. Who said that? Good job. Great. Now we get different behavior. This is interesting, right? So I'm comparing a very large value. This happens to just be the largest value that you can hold into an integer, a little bit more than 2 billion. Integers are 32-bit values in my compilation right now. And signed integers are essentially, 31 bits of positive values. So if we look at a 32-bit value, that's about 4 billion, so half of that is about 2 billion. So yeah, the maximum integer, there we go. So we are actually printing that out, and we're saying, hey, is it less than 3? And then we're going through and doing other stuff. And you can see, this is cool. We're actually, we're comparing against that, because sure, some of the initial values are that, but then we're moving on and comparing versus the other values. So now things are actually starting to look good. So we've initialized our values. Now I can almost guarantee, I have pretty high confidence that Valgrind would pass this. Famous last words, you should actually test that. Confidence means nothing when it comes to code. Your code doesn't care about your confidence, I'll put it that way. Okay. So we actually have something that seems like it's doing something that may be interesting, may be right. So I'm going to go through and implement Git now that I have something that I feel may be providing some utility, something right. So certainly in Git, this one I'm going to make a little bit more terse so that you see a contrast between the terse version and kind of the longer version. I feel like the longer versions are usually easier to read. Writing code is not a challenge to make things small. Writing code is a challenge to make things readable and understandable and debuggable. Writing code that works is not the hard part. Writing code that you can live with for long is the hard part. So emphasize that. Code craftsmanship is important. Read my post on code craftsmanship. Okay, sorter Git. I know I have my sorter. I know it has data. Within that data, I know I have values from the start to end. So I will create one variable, which is the initial start, and that is the start. Okay, fine. And I will get the data at that start value, right? Actually, I made the wrong thing. I can do this a little bit easier. I will just say this is the val that I want to return. And I will say that my val is that piece of data at the index for the start of the data within the array of data. Fine. And then I will simply say s start plus plus. This is terse, right? I have a whole bunch of dereferences, I have a whole bunch of operations all on the same line. This is fine. I'm not going to say this is wrong code, and for kind of people who are used to looking at C, this is typical. You don't bat an eye. However, I just want to compare that versus a lot of lists where we're avoiding using indexing into the start structure with pointers all the time, and instead just creating a variable that you don't need to think about pointers, dereferences, and all of that. You can just look here and see, oh, yeah, okay, this is end minus start, right? So I just want to leave this like this to kind of contrast the two, right? Okay, and then here we can say return the value. Why aren't some values in the array int max? The values in the array aren't int max because as we add more values, we replace the int max with those values. I'm not saying this code is correct, so we're going to have to debug a little bit more. But I'm just saying that, we have something that looks a little bit along the correct path. Because I'm done debugging the add, I'm going to remove this. After you're done with print statements, get rid of them. Too many print statements means that you're debugging not the programming, you're debugging horrendous amounts of print statements to try to figure out what's happening. It doesn't take long to write out a new print statement. It takes a long time to parse through 10,000 print statements. Optimize for the right things when you're developing. So let's see what happens here. Wow, it works. Cool. Why do I say it works? We're adding a 3, we're adding a 1, we're adding a 2. We're adding them not in sorted order, and it spits back the values one at a time in sorted order. This is making a lot of assumptions that you'd never add after you get. This is making a lot of assumptions. This is a bad data structure, right? But yeah. Zombie comment, never getting here. What do you mean zombie comment? Elaborate on that, please. Oh, yep, you're awesome. Woot. This is the problem with adding these things. I would not have added that comment when I was really writing code. What I might add if there are parts here, so I'm implementing this and testing out things. I need to get some functions working. I want to get some implementation. If I have other features that I really want to add, and I know I'm going to have to add, but I want to test this and get it all working first, I add explicit to-do statements. So to-do, add the ability to add after we've get, right? After we've called get. So I don't provide that functionality yet. I'm adding this to actually do that, to actually notate to myself to do that. Better would be to actually say, I'm making an assumption about the code right now. I'm not going to go into why you can't call add after you call get. You can just go through the code, but I am really making that assumption. So I'm making an assumption. If I'm making an assumption, I should add an assertion so that I catch myself if that assumption is invalidated, right? That's what assertions are for. So where could I add that assumption? I know that start is being iterated here and end is being iterated here. A proxy for saying I'm assuming that no gets have happened at this point is whether start is equal to 0. So because I am making that assumption, I better have an assertion for it. And if I look at this, great, I don't trigger the assumption. However, if I were to go down and try to do a little addy, I get an insertion. So here you can see that the assertion is actually really cool. It's telling me what C file, what C file the assertion triggered in, what line within that file it triggered in, and it prints out the actual assertion condition, why it failed. Assertions are great. And it dumps out your entire program, does a core dump. Core dumps are nice because you can use GDB to actually jump into the core dump and figure out the state of the program at the time. I'm not going to go into that probably for a while. So anyway, I'm going to leave it at this. We do need to actually expand out this program, but I'm not going to do it now because we don't need to make the point that I'm trying to make. Also, destroy doesn't need to work for the point that I'm trying to make. But I'm going to add to do, do this function. Great. So I've kind of annotated my code, the things that I haven't done, I've noted that I haven't done. And I've even added some checks where things that I know will break, check to make sure that I'm not using the program in a way where I know it will break. Great. So now I have an implementation of this for integers. My point here is we have a sorter and it works for integer values. What we want to do is create a sorter that does not work for integer values. Instead, it works for void stars, i.e. our generic type. It works for any type that we want to pass in, right? Okay, so I don't know if I would encourage you to do this. I always like seeing returns in functions. This is just a style thing. I like explicitness. I like a lack of ambiguity. So add return even if it's not needed. I might as well. Actually, I'm surprised that this is okay. If I compiled with warnings, this should complain. So I'm not implementing the function, so I'll just return an error. If I wanted to do this correctly, I might do something like no sup. This function is not supported. I'm not going to go into the details about this here. I just wanted to detect this one thing. Yep, so I need to add as well error no.h, because that's where the error types are defined. I mentioned them earlier. You can check them here. Not sup. No sup. So it's not sup. Okay, fine. So I just want to make sure that I got rid of that one error. So here, my first error has to do with comparisons and values and integers and all that stuff. So we're to the problems that would actually happen if I actually just change this from ints to void stars, right? Nope, 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 nope. Here, great. Okay, so again, if we try to compile that, we get a whole bunch of errors because we've now changed it to take void stars, and we aren't using void stars really anywhere else in the program. So what I'm going to do is generate, I'm going to use the integers, but I'm going to use pointers to integers. These could be pointers to structures, they could be pointers to other things, because this is all generic, right? So, yeah. Interesting, you're getting interrupted by ads? Okay, I don't know how to use Twitch. I was hoping ads would not be enabled. I didn't explicitly enable them, so that's not great. If anybody does use Twitch, tell me about that, because I don't know, I didn't know that ads were enabled, and I'd like to get rid of them. So anyway, I'm going to add my, let's call it something else to not be ambiguous here. All the data. Bad name, but it's fine. We aren't going to be using it that much. So I'm going to say that I'm going to create an array just to mimic the behavior that we've seen so far, and that array is going to hold ints, and the array is going to hold ints in the same order that we have them here. And now what I'm going to do is I'm not going to pass the integers in explicitly. I'm going to pass in a pointer to the first item in the array. Actually, you know what? Hey, we're going to go through an array. When you're going through an array, you should use a for loop. Don't have redundant code if you don't need it. It's bad. While I is less than 3. 3 is also kind of bad here, but I'm not going to change that. That should be defined as a constant value somewhere in the very least, sorry. So, great. So I'm going to insert all of the data that I initialized here. So here I'm just creating an array with 3 items in it that are the integers 3, 1, 2. I'm passing pointers, so this is very important here. I'm passing a pointer to each of those things into the sorter add. So now these are void stars, and then I'm getting those things back within sorter get. Okay, now sorter get returns a void star, so it's going to get angry at us here because D prints an integer. So I'm going to actually cast that to an int, but it's wrong. It's actually a pointer to an int because we are passing in pointers to integers, right? And then I'm going to dereference it because I actually want to print out the integer itself. So let's see if all of the compiler errors are gone in main. Cool, I have many fewer problems, and a lot of these have to do with other problems, with the comparison stuff that we're actually going to address here, right? Oh, okay, so yeah, that's a problem. Use an ad blocker. Ad blocker should help with this, and if you have Amazon Prime, then just attach your Amazon Prime account to this, right? Yes, absolutely. So that's the problem. Very well cited. Okay. So one problem. Let's actually dive into the details here. Okay. So warning: return makes a pointer from an integer without a cast. Right. So I know that this is in function pointers on line 98. If I go to line 98, I see. Oops. If I go to line 98, I see this. So it's saying that this is making the return makes a pointer from an integer without a cast. We know that we're returning a pointer, so that's why it's saying it's casting to a pointer, and it makes it from an integer because, as you said, val is an integer. So if we just change val now to what it should be, then we should be able to get rid of that error. Yes, great. So now we start having a lot of the errors that are all, well, we actually still have one on line 95. That was, let's check what that is. 95. So on line 95, we're setting val equal to sdata start. Ah, okay. This is where C gets really, really weird. Okay, this is where, like, you might just need to look at the code. I'm going to say what the problem is here, and you're going to need to kind of go through and figure this out. So one, it should be obvious that, like, okay, now I'm storing void stars, I should change this to void star. And if I change it to void star, then I should change everything to that, right? So I'm allocating my data. It's now void star, fine. I'm changing all of my data now to int max. Ooh, that's weird. So let me just initialize it to null instead. That's going to cause problems. It means that we're going to have to deal with the case where we're comparing against something that's null. So we'll keep that in mind for later. But for now, I think that should improve some things. Ooh, it made things much, much worse. Awesome. Value not a... Yeah, okay. So the second thing, and this is where a lot of our problems are going to come in, is that we are trying to make an array here. An array is the same thing as a pointer. A pointer can point to an array, and when we take an index from that pointer, we're indexing into the array. However, here we have an array. This says basically that data is an array. That's fine. But we're supposed to have an array of pointers. So I need to add an additional pointer here. This says I have pointers. Well, this says I have an array. And this says that array is of pointers to void star. Okay. So again, this is a little obtuse. You might want to pull the code from this repo and look at it yourself a little bit more. So I'm hoping that fixes a lot of these, but yeah, it fixes some. Great. Okay, now we have some problems here in data I. So I probably actually made accidental mistakes here. So data I. So now data is actually a pointer to a pointer, and is actually a pointer to an array of pointers, and now we get rid of all of the problems in there. So all of the problems right now are between line 71 and 80, which is within kind of the function that we actually want it to be in, right? So what I just fixed here is that we're actually asking to allocate something, which is an array, so it should be a pointer, but then remember that it's a pointer to pointers, right? So this should actually be that we're allocating something that is tracking void stars, right? Okay, great. So now we're at a point where most of the errors are within add. So now we're at the point where we're like, okay, here we have this really simple operation where we're trying to compare two items within the array. But how the heck do we do that? Because all that we're passed in now is these void stars, and void stars are generic. We don't know what those are. The data structure for the sorter doesn't know what those are. So here's where we have to take kind of the trick from qsort and say what we need to do is have the user pass in a function pointer. So a function pointer, I hate to say it in C, just has horrible syntax, and the syntax is 100% why I didn't make you do this in the homework. But I figured, you know, it's useful to go over here. So the syntax for that is I'm going to want the function to return an int. This is a function pointer that I'm going to call function. Actually, let's call it something a little bit more reasonable and to the point for what it's supposed to do. Let's call it the comparison function. And that function is going to take in a void star that we're going to call A, and a void star that we're going to call B. So this is the syntax for saying I want to take a function as an argument. This is confusing, and I'd like to kind of shuffle that away into the file cabinet of your mind, and let's look at how to actually use that, because using it is where it might get a little bit more obvious. So first I need to define the function. So it returns an int. The int is basically going to say yes or no, is it less than or greater than the thing, the other value, right? Okay, and this is my integer comparison function, right? Because it's comparing, I'll say int pointer, because we're taking pointers to integers, right? So I'm defining my int pointer comparison function. I know that this is supposed to compare what is two void stars that are void A and void B, and I know that both of these are integers, so I'm going to call this, I'm just going to change the variable names to a int, and I'm going to set that equal to the casting of A. I'm going to make this a little bit. Let me clean this up. So AI equals A, BI equals int B. So I know these are int pointers, sorry. So I can cast them explicitly. I actually don't need to. I could just set them, because you can set a void star essentially to anything. And what I'm going to do is just return whether AI is less than. I know I have an int here. Actually, let's actually make it an int. Let's make this even easier. So let's just return whether AI is less than BI. Now remember, I'm returning a predicate here. I'm returning a comparison. Comparisons, less than, greater than, all of that, return 0 or 1. So this is actually going to return an integer, which satisfies this requirement. Okay. I think do you have to dereference twice? Compare function. It's a good question. We'll see. Don't think they need to match. I don't know what you're referring to there. Okay, so now sorter add the last argument is now our function pointer. So int pointer compare function. This is the name of my function. So I'm passing the function in as an argument. This is what you do in functional programming all the time. Look, Ma, we're doing functional programming in C. It's just, obtuse syntax for doing it. But you do this in C. You pass functions to functions. So that's what this hopefully looks like. So now in our add functions, we're taking our comparison function. We've defined our comparison functions, our comparison function that takes pointers to integers. And now what we're going to do is, instead of this custom code that is assuming integers, we're actually just going to call our comparison function on temp and val. Now, I don't think this is going to work, and it's not going to work in an annoying edge case that we're going to need to deal with, but it's going to come close. Let's see how it does. Oh, I was not expecting this. Makes a pointer to an integer, so temp is probably an int. Yes. Void star. And then val is a void star, so that should be fine. Okay, where else do we have a problem? Oops, not 17, 71. So we're taking the array. This should be a double pointer. That might have been what you were referring to in chat. I appreciate it if you were. Assignment from incompatible type, so this is probably an int versus void thing, again on 71. Interesting, that's not what I was expecting. That's where I just made the change, so I'm missing some logic here. So I know data is a pointer to a, oh, well, okay. Experienced people make dumb errors too. Everybody makes dumb errors. Okay, 107 is the error here. Great. So now I'm down. I've made it past at least warnings within there. Notice, all these are warnings, but warnings are really important. You get rid of warnings. Warnings say that there's probably a problem. So it's important to actually address them. Okay, so the assignment makes a pointer from an integer without a cast. So I have a void star here that we're passing in. Let me see how that's being passed in. So that is actually just a void star that's being passed in. It's a pointer to a value. So I'm casting that to a pointer to an integer, and then I'm dereferencing it. So the problem here is that I'm actually dereferencing it and I'm getting the ints. So the AI and the BI are the actual ints that are being dereferenced. Okay. Let's see what happens. Blah, segmentation fault, core dumped. Okay, so what do you do when you get a segmentation fault? First, notice that I am compiling with the G flags. That means that I should be getting good debugging information. So I can run GDB on it. So let's dive very quickly into GDB and see what we can do. I actually sometimes forget how to use GDB, so let's see if I have it right. So we run GDB, we ask it to actually run the program, and we see that we have gotten our segmentation fault. And we see that it says that it's actually in our function, our comparison function. We're dereferencing. Let me see if I can get my pointer here. No, there we go. Oh, I'm sorry, I hid my pointer, so I'm not going to be able to specify where this is. But you can see on the line where it's saying where the fault is at, on line 107, it's saying that A is 0. 0 is null. So yeah, we're actually receiving one of the pointers which is null, and we're trying to dereference null. Note that if I wanted to see how I got to this point within the function, I can ask for a backtrace, and it tells me that from main on line 122, I called a function sorter add, and on line 78 within that, I called int pointer compare function, and then on line 107, I get all of these problems. So yeah, GDB is great, folks. Don't print stuff when you get a seg fault. Drop it to GDB when you can. Great. So I know that essentially this A is being passed in as null. You know, I don't want that to be part of the API. I don't like that as a constraint, so I'm going to actually just assume that A and B are not null. So now I'm actually going to just replace what I had with an assertion, and I'm going to try running it again. And once I execute it, now I get the assertion, and it tells me early on where the problem is, right? And that's what I want. I want an early failure, exactly where the issue is. Now, I said that there was a problem with this, and the problem is exactly what I showed you. That temp, that first value, will sometimes be null. And actually, as we kind of iterate through the array and keep pushing values further back in the array, we're always going to end up at a null value at the end, where we've created kind of the new space, right? So because of that, we just need to change this a little bit, where if we have null, then we kind of know that we should go on and replace the null with a real value. So if temp does not equal null and the comparison function, then continue. But if temp equals null, then we know we want to replace it, right? So let's actually do a little bit of that, do a little bit of that. Cool, it works. So now we have a generic data structure that can sort arbitrary values that are passed in as void stars simply because we provided the function that's customized to understand how to compare values of the type that we're passing in. And the client is the one that understands what that type is. It's the one who provides that function that's customized to int comparisons, or pointer to int comparisons. And it's the one that decides what to actually add into the data. In this case, it's adding our pointers to our integers, right? So this is what I've been talking about a lot in class and on Piazza about if you want to make a generic data structure, you often need to do this. I want to remind you that in Java, like it kind of looks the same. You're providing this comparator object that's able to compare things of the specified type. We're just doing the same. We're just providing the function pointer, right? It's getting late, so I don't want to continue with this. I'll continue with function pointers and XV6 and all of that next time. It's probably enough to talk about in one of these sessions, so that's perfectly fine. I will commit all this code. You can look at the pre and the post commits to see all the changes that we've made. I'm not going to go through and implement the rest of this because it's not relevant for kind of the lesson that we're talking about here. But I hope this was useful to people. Again, I'm sorry it went long. I will learn how to use my time better with this, but scoping leads to a proper time unit is obviously very hard for me. So thank you all very much. I hope this was useful. Let me know tomorrow if it was or was not. Let me know what I can do better. And have a good night all. Thank you all.